Welcome back, everybody. Learning as a hobby here. I want to do the solutions to um, selected exercises from Chapter 7 in Spivak's calculus today in this video. So that's what we'll do. And then the next video will be the summary, my chapter summary for Chapter 8 in the book, which is a relatively long chapter. So that's going to take me a little bit of time to write up uh, my summary. Then there's the exercise set, and then there's also an appendix to Chapter 8, which is on uniform continuity with its own exercise set. So we still got a little bit left to do in section 2, but we're getting there. We're getting to the end. I mentioned this in one of my vlogs also, but after I finish Chapter 8, which is the last chapter in section 2 of the book, I want to do I want to get through the elementary stuff not the elementary stuff, sorry, the foundational stuff in Tao's book. So there's Chapter 3, which is on some set theory stuff. Then in the next chapter, he constructs the rational numbers, sorry, the integers, and then the rational numbers. And then the following chapter, he constructs the real numbers. And I'd like to do Tao's construction of the real numbers and Spivak's construction of the real numbers at the same time. So I'll make two different videos, and I'll talk about the differences between them, I guess, in that video. That's coming up, but the next video after this will be the summary for Chapter 8 here. So anyway, let me get right to my solutions to some of the problems in Chapter 7, because that's what you're here to look at, I guess. So let me bring up my solutions, and we'll just go through them one at a time. A lot of problems in this section are relatively straightforward. For example, question number 3 are basically pre-calculus problems. As you can do these as long as you know the intermediate value theorem. Let's just go through it anyway. So question 3 says, prove that there's some number x such that there's two parts to question 3. So part 1 says, show that there's a number x such that x to the 179 plus 163 over 1 plus x squared plus sine squared x is equal to 119. And like I said, it's just an application of the intermediate value theorem. So what I'm doing is constructing a new function that I'm calling f of x, which is equal to the left-hand side of the equation minus the right-hand side of the equation up above. And since all the pieces in that function are continuous over the real numbers, the function itself is continuous over the real numbers. And if you plug in 0 in for x, notice that you get a positive number. If you plug in -2, notice that you get a negative number. And that's all you really need. So by the intermediate value theorem, f has a root then in the interval from -2 to 0. So you just have to pick two numbers that work. And that's it. That's part 1. Part 2 is exactly analogous, except just a different equation. So here in part 2, he wants us to show that there's a real number x such that sine of x is x minus 1. I won't belabor this just because it's very similar to the one I just did. But, define g of x equals sine x minus x plus 1. This is a continuous function for the same reason that the one in part 1 was. And then you just pick, convenient values. G of 0 happens to be positive, G of 3 happens to be negative. So again, by the intermediate value theorem, that means that G has a root in the interval from 0 to 3. All right. So like I said, those are basically like pre-calculus problems. Question number 4 he says is a continuation of problem 3.7, which is, I'm sure I did that problem in my solutions to Chapter 3. So if you want to see that question, you can go back to my videos on the exercise sets from Chapter 3. But anyway, we'll just jump right into the problem that's here. So part A says, if n minus k is even and greater than or equal to 0, find a polynomial function of degree n with exactly k roots. So I just constructed one. right? So here I'm constructing the polynomial f of x, which is I'm defining to be x squared plus 1 raised to the n minus k over 2 power. That's an integer because we're assuming that n minus k is even. So that gives you an integer. But notice, and then I'm multiplying that by x minus j, where j goes from 1 to k. Notice this has exactly k roots, right? The k roots are 1, 2, 3, all the way up to k. The first factor here, x squared plus 1 to the n minus k over 2, has no roots because there's no real value x that makes x squared plus 1 equal to 0. Therefore, this has exactly k roots, right? And for part B, a root a of a polynomial function f is said to have multiplicity m if f of x equals in parentheses x minus a to the m times g of x, where g of x is a polynomial function that does not have a as a root. So that's just a definition of what it means for a root to have multiplicity m, which again you probably went over whenever you did pre-calculus, or maybe even in algebra you did it. Let f be a polynomial function of degree n. Suppose that f has k roots. Counting multiplicities, for example, suppose that k is the sum of the multiplicities of all the roots. Now he wants us to show that n minus k is even. So I did this by contradiction. Right, here's my proof. Assume for the sake of contradiction that n minus k is odd. Right, we want to show that n minus k is even, but so for contradiction, though, we'll assume that it's odd, and that f of x is equal to g of x times the product of x minus xj, j going from 1 to k. So here, all the xj's are roots of this polynomial function. Not necessarily all distinct. They may have, some of them might have multiplicity bigger than 1. Where g has degree n minus k, and g of xj is not 0 for any j 1, 2, etc. up to k. By theorem 7.9, then g of x has a root, but that's a contradiction because we constructed this this polynomial to have exactly k roots with counting multiplicities, so that g of x having an extra root means that the polynomial f, instead of having k roots, now we've concluded that it has k plus 1 roots. That's our contradiction. So that means that n minus k must be even. All right. Okay, question number 5. Suppose that f is continuous on the closed interval from a to b, and that f of x is always rational. What can be said about f? So what can we say about f? We can say that f is a constant function, since if x1, x2 are elements of the closed interval from a to b, and f of x1 is not f of x2, then f being continuous on the closed interval from a to b implies f takes on all numbers between f of x1 and f of x2 by the intermediate value theorem, and that contradicts that f is always rational, because the interval from f of x1 to f of x2, or vice versa, must contain both rationals and irrationals by the density of the irrationals and the real numbers. So that's the solution to question number 5. All right. Question number 6 says, suppose that f is a continuous function on the closed interval from -1 to 1, such that x squared plus f of x all squared equals 1 for all x. This means that f of x always lies on the unit circle. He just says that as an aside. Show that either f of x is square root of 1 minus x squared for all x, or else f of x is negative square root of 1 minus x squared for all x. So here's my proof. Assume that x tilde is a root of f, and that x tilde is an element of the closed interval from -1 to 1. Then if you plug that into the equation up above, then x tilde squared plus f of x tilde squared is equal to 1, implies that x tilde squared is equal to 1, or in other words, x tilde must be either plus or minus 1. Therefore, f of x is f of x is 0 only when x is plus or minus 1. Those are the only roots for the function f. Furthermore, if you plug 0 in for x, you get 0 squared plus f of 0 squared equals 1, or in other words, f of 0 has to be, f of 0 squared has to be 1, which means that f of 0 can either be 1 or minus 1. Those are the only possibilities for f of 0. In the case where f of 0 is 1, that's obviously a positive number. The intermediate value theorem implies that f of x is greater than 0 for all x in the open interval from -1 to 1, since otherwise f of x would have a root in the interval from -1 to 1, and we know that it doesn't, because we just showed that. A similar argument shows that if f of 0 is -1, meaning negative, then f of x is less than 0 for all x in the open interval from -1 to 1. The result then follows from solving for f of x in the equation. So just since it has no other roots in this interval, then it's always negative, in other words. So you just solve for f of x in the equation, and those are the only possible solutions. All right, question number 7. How many continuous functions f are there which satisfy f of x squared equals x squared for all x? This is a very similar type of thing to the one that we just did. So here's my solution. There are 2. F of x equals x, or f of x equals negative x, which follows from the fact that f of 0 squared equals 0 squared, which is 0. So that means that f of 0 has to be 0. Furthermore, that also implies that the absolute value of f of x has to be equal to the absolute value of x. In other words, the magnitude of f f evaluated at x is equal to the magnitude of x. The intermediate value theorem tells us then that if x is not 0, then f of x is not 0. And either takes on the same sign as x or the opposite sign, and that the result just follows. All right, question 11. Suppose that f is a continuous function on the closed interval from 0 to 1, and that f of x is in the closed interval from 0 to 1 for each x. He says draw a picture. I didn't draw the picture here, but he has actually a picture of it in the book. On the side of the page. So if you have the book, you can look at it. But I didn't draw it here. Prove that f of x equals x for some number x. So it's just, again, this is just an application of the intermediate value theorem. So here's my proof. Let g of x equals f of x minus x. Then g is continuous on the closed interval from 0 to 1, because f of x is continuous on 0 to 1, and so is x. If f of 0 is equal to 0 or f of 1 equals to 1, then we're done. Otherwise, g of 0 equals f of 0 minus 0, which is f of x, that would have to be positive, and g of 1 equals f of 1 minus 1 would have to be negative. Therefore, the result just follows directly from the intermediate value theorem. All right, 12a is very similar to the one we just did as well. Part A says problem 11 shows that if that f intersects the diagonal of the square in figure 14. He says solid line. He's referring to the drawing that he has in the book. Like I said, I didn't reproduce it here, but if you have the book, you can see it in the exercise set. Show that f must also intersect the other dashed diagonal. Again, he's referring to the picture that he has drawn in the book. All right, so here's my proof. Let g of x equal f of x plus x minus 1. If f of x is strictly between 0 and 1 for all x in the closed interval from 0 to 1, then g of 0 equals f of 0 minus 1, which is obviously negative, and g of 1 equals f of 1, which is obviously positive. Since g is continuous on the closed interval from 0 to 1, g of x equals 0 for some x in the interval from 0 to 1 by the intermediate value theorem. If f of 0 is equal to 1 or f of 1 equals 1, then g of 0 equals f of 0 minus 1 equals 0, which implies f of 0 is 1 minus 0. Similarly, if g of 1 is f of 1 equals 0, then f of 1 equals 1 minus 1. So it holds in those cases too. All right. There's part B as well, which is, again, very similar to the one. This just follows from the intermediate value theorem. Prove the following more general fact. If g is continuous on the closed interval from 0 to 1, and g of 0 equals 0, g of 1 equals 1, or g of 0 equals 1, g of 1 equals 0, then f of x equals g of x for some x. So here's my proof. Again, very similar to the one I just did. Or the last two that I did. Let h of x equal f of x minus g of x, and assume that h of 0 is not 0, h of 1 is not 0. Then I broke it down into the two cases that he suggests. So case 1, g of 0 is 0 and g of 1 is 1. Then h of 0 is f of 0, which is, of course, positive, and h of 1 is f of x minus 1, which is obviously negative. Therefore, it follows from the intermediate value theorem. Case 2, let g of 0 equal 1 and g of 1 equal 0. Then h of 0 equals f of 0 minus 1. Again, obviously that's negative. And h of 1 is f of 1. Again, that's obviously positive. The result follows in case 1 and 2 result follows in case 1 and case 2 by the intermediate value theorem, right? G has to have a root in the interval from 0 to 1. So that means that two functions are equal somewhere in that interval. So, and then finally, if h of 0 is 0 or h of 1 is 0, then the result is clearly true. And that's it. So those three questions that we just did are very similar to each other. All right, question 14. If f is a continuous function on the closed interval from 0 to 1, let he calls this the maximum value of absolute value f on the closed interval from 0 to 1. And there's a few parts here. So part A says prove that for any number c, we have that the maximum cf is equal to the absolute value of c times the maximum of f. Right, so let's prove that first. Let f be continuous on the closed interval from 0 to 1, then so is the absolute value of f. Then absolute value of f achieves its maximum on the closed interval from 0 to 1 at some x0 in the closed interval from 0 to 1. That's from I think it's theorem 3 in the chapter. Then for any y in the closed interval from 0 to 1, absolute value f of y is less than or equal to absolute value of f of x0, because that's the maximum, right, for f. That implies that if you multiply both sides of that inequality by absolute value c, which doesn't change the direction of the inequality because absolute value of c is non-negative, then you get basically what you want. So absolute value c times absolute value f of y is less than or equal to absolute value c times absolute value f of x0. And then just using the definition of, how the function algebra, right? That gives us what we want. So the absolute value c, that's the same thing as absolute value cf of y less than or equal to absolute value cf x0 for all y in the closed interval from 0 to 1. Therefore, the maximum of cf is equal to the absolute value c times maximum of f. Right, part B says prove that the maximum of f plus g is less than or equal to maximum of f plus maximum of g. And he also wants us to give an example where maximum f plus g is not equal to absolute value f plus f. I'm sorry, maximum of f plus maximum of g. I just gave the example here because I forgot to write it when I was writing it down, and I didn't feel like moving everything down and everything. So if you just take the example f of x equals x and g of x equals negative x, you'll see that that's an example that works. But here's the proof of the statement. So max f plus g is equal to the maximum over 0 to 1 of absolute value f plus g, which is equal to f plus g of x0 for some x0 in the closed interval from 0 to 1. And that implies that the absolute value f of g plus x0 is equal to absolute value f of x0 plus g of x0. By the triangle inequality, that's less than or equal to absolute value f of x0 plus absolute value g of x0. By definition, that's absolute value f of x0 plus absolute value g of x0, which is less than or equal to maximum f plus maximum g, right? Just by the definition of max f and max g. So that shows part B holds. Part C says prove that max h minus f is less than or equal to max h minus g plus max g minus f. This is very straightforward. It's just the triangle inequality. Let f, g, h be continuous functions on the closed interval from 0 to 1. Then max h minus f is the same thing as max h minus g plus g minus f, which is less than or equal to max h minus g plus max g minus f. That just follows from what we showed up here, right? From part B. Okay, question number 15. Suppose that phi is continuous and that limit as x goes to infinity of phi x over x to the n equals 0 equals limit x goes to minus infinity of phi of x over x to the n. All right, part A says prove that if n is odd, then there's a number x such that x to the n plus phi of x equals 0. All right, so here's my proof. Limit, and I should say before I start this is very similar to one of the proofs of one of the theorems from the book. Actually, part A is similar to one of the theorems, the proof of one of the theorems of the book, and part B actually is also similar. He actually says in the question, he says, look at these theorems in the book. So he gives you a suggestion on how to do this. But anyway, since limit x goes to plus minus infinity of phi of x over x to the n equals 0, there's a delta greater than 0 such that for all for 0 less than absolute value x less than delta, absolute value phi of x over x to the n is less than 1/2, which implies that negative 1/2 is less than phi of x over x to the n less than 1/2. Add 1 to all three sides, or actually we only care about the bottom half, but so you add 1 and you get 1/2 less than 1 plus phi of x over x to the n. Okay, and then choose x0 in the interval from 0 to delta. That implies that 0 is less than, so just multiply through this inequality by x0 to the n. Then 0 is less than x0 to the n over 2, less than x0 to the n times 1 plus phi of x0 over x0 to the n. That's equal to x0 to the n plus phi of x0. Right, so that's a positive value for the function. Next, choose x1 in the interval from negative delta to 0. Then 0 is greater than x1 to the n over 2, greater than x1 to the n times 1 plus phi of x1 over x1 to the n, which is the same when if you distribute, that's the same thing as x1 to the n plus phi of x1. I got that just by multiplying by x1 to the n on both sides of this inequality again over here. Then f of that's a negative number, right? Obviously, it's less than 0. So then f of x1 is less than or equal to 0, is less than or equal to f of x0, and f is continuous on the interval, the closed interval from x1 to x0, which implies there's a y in the interval from the closed interval from x1 to x0, such that f of y is equal to y to the n plus phi of y equals 0, but by intermediate value theorem. Okay, part B. Prove that if n is even, then there's a number y such that y to the n plus phi of y is less than or equal to x to the n plus phi of x for all x. In other words, prove that there's a minimum value. Okay, so here again, this is very similar to one of the proofs of the theorems in the chapter proper. Choose b greater than 0 such that absolute value of phi of b over b to the n less than 1/2. Basically same thing I did up above in part A. Then 0 is less than b to the n over 2, less than or equal to b to the n plus phi of b, and 0 less than negative b to the n over 2, less than or equal to negative b to the n plus phi of negative b. That's because n is an even power, right? Since f of x is x to the n plus phi of, did I write k there? That should be x. Phi of x is continuous on the closed interval from negative b to b. It takes on its minimum value at some y in negative b to b. That's a result of one of the theorems in the chapter. Therefore, y to the n plus phi of y less than or equal to x to the n plus phi of x for each x in the closed interval from negative b to b. Furthermore, y to the n plus phi to the y is less than or equal to b to the n over 2, which is less than or equal to x to the n plus phi to the x for all absolute value x greater than b, and that gives you the result. Right. Like I said, both of these proofs are very similar to ones that he did in the chapter itself. I forgot what number of theorems they were. They were like the last two or like the last three or something theorems in the chapter. Okay, question 19, part A. Suppose that f is continuous on the closed interval from a to b, and let x be any number. I don't know if you guys can hear that. There's a car blasting their radio outside. Sorry, let me start over. Part A, suppose that f is continuous on the closed interval from a to b, and let x be any number. Prove that there's a point on the graph of f that is closest to the point x comma 0. In other words, there's some y in the closed interval from a to b such that the distance from x comma 0 to y comma f of y is less than or equal to the distance from x comma 0 to z comma f of z for all z in the closed interval from a to b. So here, this is my proof. Here I define this new function. It's not exactly the distance. If you just take the square root of this, you get the distance. I just didn't feel like writing the square root over and over again, so I just used the square of it as my function g. But they have the same properties. So when the square root of g of z is optimized, so is g of z, and so I just didn't feel like writing square roots all the time. But anyway, here define g of z equal equal z minus x squared plus f of z squared. then G is continuous on the closed interval from A to B, therefore has a minimum value G of Y for some Y in the closed interval from A to B. All right, that's from one of the theorems in the chapter. I think it's theorem. Is this the minimum? I think that's theorem 7 actually in the book. All right, question part B of the question 19. Show that the same assertion is not necessarily true if the closed interval from A to B is replaced by the open interval from A to B throughout. So here I'm constructing something that does that. So consider f of z equals 0, identically 0 for all z in the open interval from A to B, and choose x equal to b plus 1. Assume there is a y in the open interval from A to B, such that y minus b minus 1 squared plus f of y squared less than or equal to z minus b minus 1 squared plus f of z squared for all z in the open interval from A to B. Then y minus b minus 1 squared is less than or equal to z minus b minus 1 squared. In particular, if alpha is some number in the interval from y to b, the open interval from y to b, then b plus 1 minus, I just switched the direction here, but because you're squaring, it gives you the same thing. So, but it's just more convenient to write it in that opposite direction. Then b plus 1 minus alpha squared greater than or equal to b plus 1 minus y squared implies that b plus 1 minus alpha greater than or equal to b plus 1 minus y. I can do that because they're positive, right? If b plus 1 is greater than alpha, and b plus 1 is greater than y for all values in the open interval from y to b. So you just get, when you take the square root, you get a positive number and the inequality is preserved and everything. That implies that alpha is, so here if you subtract b plus 1 from both sides and then multiply through by a minus 1, that says that alpha is less than or equal to y, which is a contradiction because we assume that alpha was in the open interval from y to b. All right, so that proves this one, part B. Part C, show that the assertion is true if the closed interval AB is replaced by R throughout. So here's my proof. Let G of Z equal Z minus X squared. Again, I just left out the square. I just didn't feel like writing the square root, but this is just the square of the distance. So, but if the square of the distance is minimized, so is the distance. G of z equals z minus x squared plus f of z squared. Then G of z is greater than or equal to 0 for all z in R. Furthermore, G is continuous on R. Choose b greater than 0 such that b plus x is greater than 0 for all absolute values z minus x greater than b. 0 is less than b squared equals here I'm just adding 0, right? B squared is the same thing as b plus x minus x squared, which is less than z minus x squared, which is less than z minus x squared times 1 plus f of z over z minus x squared. All right. Also, G is continuous on the closed interval from negative b plus x minus x to b plus x, and therefore takes on its minimum on that interval. Furthermore, G of y is less than or equal to G of z for all y in that interval. Z in the union of these two intervals, therefore G takes on its takes on its minimum value on the entire real line. Okay, again, this was a very kind of similar proof to one that was in the chapter. All right, part D, in cases A and C, let G of X be the minimum distance from X0 to a point on the graph of F. Prove that G of Y less than or equal to G of X plus absolute value X minus Y, and conclude that G is continuous. So here's my proof. Let G of X equal the minimum over the interval from A to B. Here I am using the square root because I need to talk about distances here. You can't get away with the square here because you end up having, if you draw the picture, you'll see why. You end up with a triangle. So I didn't want to talk about squares of distances. I wanted to talk about distances. So anyway, let G of X equal the minimum of the closed interval from A to B of square root f of z squared plus z minus x squared. That's equal to square root of f of z star squared plus z star minus x squared for some z star in the interval from A to B, the closed interval from A to B. Okay, then the square root of f of z star squared plus z minus y squared is less than or equal to square root of f of z star squared plus z minus x squared plus the absolute value of y minus x. This follows from the triangle inequality. I didn't draw the picture here, but you'll see if you draw the picture, you'll see what it's because these are legs of a triangle. So I'll just say draw the picture if this is not clear. All right. Therefore, g of y equals the minimum over the closed interval from a to b of square root f of z squared plus z minus y squared less than or equal to g of x plus absolute value y minus x. That's because this thing here is g of x. Right. Furthermore, so here the other part of the question was he wants us to conclude that g is continuous, so we can prove that now that we have that result. Furthermore, this implies that absolute value g of y minus g of x less than or equal to absolute value y minus x for all xy in the closed interval from a to b. Then if we fix x in that interval and take 0 less than absolute value y minus x less than delta less than epsilon, then absolute value g of y minus g of x is less than or equal to absolute value y minus x less than delta less than epsilon. Therefore, g is continuous on the closed interval from a to b. An identical proof shows that the proposition holds for r, but I skipped doing that because it's the same, similar type of thing. So simply replacing closed interval a to b with r. All right, so I skipped the proof for r just because it's similar. Okay, part E says prove that there are numbers x0 and x1 in the closed interval from a to b, such that the distance from x0, 0 to x1 f x1 is less than or equal to the distance from x0 prime 0, comma 0 to x1 prime, comma f of x1 prime for any x0 prime, x1 prime in the closed interval from a to b. All right, the proof just follows directly from theorem 7. So since g is continuous on the closed interval from a to b, this follows directly from theorem 7. From theorem 7, I'm talking about the theorem 7 from chapter 7. Right, maybe I should have specified that, but this from theorems maybe 7.7 I could write. All right, I think this is the last one I did. There were 2 parts to this, but I think I stopped at part A just because I want to get on to chapter 8 already. It's been a while. So this is the last one though that I did. So 20A, suppose that f is continuous on the closed interval from 0 to 1 and f of 0 equals f of 1. Let n be any natural number. Prove that there is some number x such that f of x equals f of x plus 1 over n. He gives a hint here. He says consider the function g of x equals f of x minus f of x plus 1 over n. I mean, we've been doing similar things like this for all the exercises before this, so that might even occur to you without the hint. But what would be true if g of x is not 0 for all x? All right, so here's the solution. So assume for the sake of contradiction that g of x equals f of x minus f of x plus 1 over n, not 0 for any x in the closed interval from 0 to 1, and for any natural number n, then g of x is either greater than 0 for all x in that interval, or g of x is less than 0 for all x in that interval. Without loss of generality, we can assume that g of x is positive. If not, we can just take the negative of g, and it's the same proof we'll go through. For all x in the closed interval from 0 to 1, then f of x, that would mean that f of x is greater than f of x plus 1 over n for all x in the interval from 0 to 1, the closed interval. In particular, f of 0 is greater than f of 1 over n, and f of 1 over n is greater than f of 2 over n, etc., all the way down to f of n minus 1 over n greater than f of 1. But that contradicts the fact that f of 0 equals f of 1. Therefore, that can't possibly be the case. So the result follows by contradiction. And like I said, I think that was the last one I did. So that's the exercises that I did from chapter 7. Let me stop the share here for a second. So like I said, in the next video, which I hope I can get around to this weekend, will be my summary for chapter 8 in Spivak. So keep a lookout for that. And after that, we'll do the exercises for chapter 8. Who knows if I'll be able to finish that over the weekend, but I'll do my best. So let me know what you guys think down below, and I'll see you in the next video. All right, guys, keep learning.